freeze. Frostbite consumes limbs. Death in the extreme cold is just a mistake away. Yet, a small city thrives atop 9,000 feet of ice. A probe hurtles through the blistering cold of deep space. A ship opens a lifeline in the frozen sea. Now, Sub-Zero on Modern Marvels. If you're able to withstand its icy grip, the cold can be a gateway to both material and spiritual enrichment. From the billions of barrels of oil pouring out of the North Shore of Alaska, to communities accustomed to minus 40 degrees Fahrenheit.
It's just living in a place that automatically challenges you and is frankly never very boring.
To science.
When you dig down into the ice, you'll be looking at ice that was formed 1,000 years ago, or 100,000 years ago, or 500,000 years ago.
To recreation.
Cold temperatures are exhilarating. You're pushed to the edge. You got to be focused all the time. You make a mistake, you're going to pay.
Shelter in these cold and often barren locales has always been a challenge. Few places on Earth offer as many obstacles to building and sustaining a structure as the South Pole. The geographic South Pole, the bottom of the world, sits atop more than 9,000 feet of snow and ice. Temperatures during the austral winter can dip to minus 117 degrees Fahrenheit. And the ice beneath your feet is literally moving, drifting 33 feet a year. So why build anything at the coldest, most remote locale on Earth?
Turns out that because it's so dry and it's 10,000 feet elevation, South Pole Station is one of the world's best places for certain kinds of astrophysics. Particularly study looking back in time at the early moments of the universe, looking at the afterglow from the Big Bang.
Research at the South Pole has included everything from global climate study to rover testing for Mars missions. Since a multinational study of the solar and terrestrial environment, known as the International Geophysical Year of 1957-1958, the United States has maintained a science base at the South Pole. It's an ideal place for science, but it's a cold hell for the buildings that house the scientists.
People knew that buildings had a very short lifespan at Pole. The snow starts accumulating as soon as you put something on the surface. Mother Nature tries to cover up that scar, and it'll drift very quickly right to the top of the structure.
By the time the 1957 buildings were replaced in 1975 with a geodesic dome structure, the first base was buried under 25 feet of ice and snow. The dome did not fare much better.
The dome, that was like Humpty Dumpty. Once it got snow on the side of it, the bottom ring cracked, the pieces started coming apart. It was impossible to put it back together again.
The challenge was to come up with a design that could extend building life past 20 years while accommodating a growing population, 250 people, almost 10 times that of the original station. In 1992, the design task went to Ferraro, Choi and Associates. They came up with an 80,000 square foot, two-story, $150 million station to be elevated 3 meters above the snow on columns that extend down to a raft foundation. A giant raft that moves with the slowly drifting ice. The building's windward face is shaped like an airplane wing to compress the wind so that it speeds up and pushes blown snow past the structure.
But after a while, the whole plateau is growing in height of snow, about 8 inches a year. And at some point in time, our building's going to be down inside of a bowl. And then the snow will start closing that bowl up and drifting on top of the station.
At this point, the new South Pole Station will be jacked up, raised in small increments by hydraulic jacks, until it is once again 3 meters above the snow. This process can be executed twice. But the intense cold is just as much a design obstacle as the rising snow. The station's external doors are 8-inch thick heated refrigerator doors.
You get condensation built up on that interface between the door and the wall, and if it's not heated, you might not be able to open that door up. It's an ice bond, and egress out of a building is critical.
In this environment, nothing can be taken for granted, especially the pace of work.
Whether it's doing a welding job or erecting a structure for a building, a little more than 2.5 times as long there as it would here.
Machines are compromised as well. The hydraulic cranes, essential for heavy lifting, are not reliable once the temperature drops to minus 40 degrees Fahrenheit.
We're still limited by temperature. You know, when we get below minus 40, operationally there becomes some problems. And when you're flying a heavy piece of steel, you don't want to have operational problems.
Selecting building materials was also a problem.
Nothing is tested for that type of temperature. So our design temperature was 100 below 0 Fahrenheit. So that was a gigantic obstacle.
The project, originally slated for completion in 2005, is a couple of years behind schedule. But since the structure's design is modular, it's being built in stages, and individual modules are occupied as soon as they're complete. As obstacles are overcome, a new South Pole station rises above the snow and ice. The current station represents the most ambitious undertaking by any nation to establish an above-surface facility in Antarctic conditions. And how long will this latest pole station last?
If the building lasted 40 years, if I'm still around, I'd be very happy.
Success for buildings in the Antarctic ice and snow is temporary. At the opposite end of the world, the preeminent craftsmen of the cold, the Eskimos, perfected the temporary structure. For the Eskimos, shelter from harsh winds and cold was a matter of life and death. But building materials in these barren wildernesses were scarce. They made winter dwellings out of what was at hand: bone, snow, stone, driftwood, and even sod.
Sod is a kind of very thick, packed earth that has a lot of plant material in it. It's ideal for insulating, for warmth.
But it's the snow house for which the Eskimos are best known.
In part of the Canadian Arctic, there was no building material, and the people needed to be out on the edge of the ice in order to hunt seals for a great deal of the winter.
Though the word igloo encompasses all forms of houses in Eskimo culture, the word is typically misunderstood to refer only to the snow house. The snow houses were temporary shelters and could be built by 2 men in the span of an hour. Using a snow knife to cut blocks from packed snow, the men would then stack the blocks into a small domed structure. The dwelling was further insulated by packing snow on the outside. Inside, sleeping platforms were elevated to reach the warmer air trapped toward the top of the dome.
And sometimes they made small cities out of these. Several groups would come together out on the ice.
The villages would vanish with a spring thaw, and the community would move on, having survived another winter. In contemporary Alaska, the Eskimos' minimalist approach to shelter has given way to high-tech solutions to beating the cold.
During the wintertime, it can be 30, 40 degrees below 0. That's almost as cold as it is in the stratosphere. We're right at the end of habitability when it comes to insulation. So we typically see something on the order of 7 to 10 inches of fiberglass insulation in walls being an economic amount to include.
But it's just as vital to protect the permafrost, the permanently frozen ground below, from the house's heat, as it is to protect the house from the cold.
Any house part that comes in contact with the soil is going to lose heat to the soil, and that might degrade the permafrost and cause a foundation failure.
Melting the permafrost can turn a firm foundation into unstable ground.
Some of it has segregated ice that are just big wedges of ice that when they thaw leave a huge gap and it can subside feet.
Elena and Joseph Ritter chose to build a top ground that's frozen to a depth of 40 feet, partly because a lot with permafrost is cheaper, but also because of the site's remoteness.
We both really enjoy the idea of having all this space and wilderness right around us.
Their house rests on an aluminum triodetic space frame, a grid braced by horizontal and vertical diagonals that form a rigid floating slab.
This is the standard for any building on permafrost. You want to keep a 3-foot airspace underneath. You know, you don't want to create any hindrance to natural convection, keeping the air flowing under the building. It's made to be perfectly rigid by the use of the 3-dimensional construction. This corner is totally subsided out from under the house, and there's no drywall cracking or any damage inside the house.
But if putting down roots in the cold is this demanding, why do it?
It's sort of an explorer mentality, it's a challenge mentality. A lot of people are just intrigued by that.
Whether it's for buildings or for bodies, comfort in the extreme cold depends on insulation. And the line between comfort and frostbite can be the thickness of your parka. In 1997, Russia's Vostok station in Antarctica reported the coldest temperature in the world, minus 132 degrees Fahrenheit. This is colder than dry ice and cold enough to make steel shatter. Sub-Zero will return on Modern Marvels. Exposure. If you're a runway model or a sun worshiper, you can't live without it. But if you're in the cold, or worse yet, the extreme cold, you can't live for long with it. The human body has a built-in strategy for dealing with excessive exposure to the cold. If the body's core temperature is threatened, it starts sacrificing the extremities, limiting blood flow to hands, feet, and even the face in an effort to protect its core temperature. This can lead to frostbite, gangrene, and if you're exposed for too long, death. Sub-zero environments aren't for the faint-hearted.
50 below is a real thing. You can go from being fine to 10 minutes later having frozen fingertips. I mean, just rock hard, frozen things you cannot do anything with.
At South Pole, I noticed that the water in my eyes started freezing. The scientist I was with had his parka down, and within about 10 minutes, the skin on his cheeks started turning black. And this is about 80-some-odd degrees below zero. So the wind and the cold can really kill you very quickly.
The coldest place on Earth, Antarctica, has featured prominently in tales of survival. Perhaps the most famous and tragic was the 1911 competition between the British and the Norwegians to be the first to reach the South Pole. Led by Robert F. Scott, the British team fell victim to poor planning, inferior gear, and ultimately, the weather. Having exhausted themselves pulling their own sleds, they arrived second at the pole and, dispirited, perished in a snowstorm on their return. By contrast, the Norwegians, led by Roald Amundsen, a consummate cold weather tactician, were first to the pole on December 14, 1911, in what was a carefully planned, almost uneventful journey. The key to Amundsen's success was that he understood dog driving, sleds, the proper cold weather diet, and fur clothing, because he had lived with and studied the Eskimos in the Arctic. He knew firsthand that the Eskimos had proven cold weather techniques and technologies.
One thing that's very distinctive about Eskimo people is this hugely inventive technology. They just seem to be able to adapt to any circumstances.
Hundreds of years ago, Eskimos were already using many of the same clothing strategies to stay warm that we use today, including creating wind-resistant and waterproof garments.
Waterproof boots in some areas were made in an incredibly ingenious way. When a seal was taken, it was gutted in such a way that all of the insides came out through the mouth.
A container was then made from the skin of the seal. These seal pokes, as the containers were known, were filled with seal oil, which was used for cooking and heating.
And then after the seal poke, after several years, had gotten very, very saturated with oil, the women would slit it in two and turn it inside out and generally dehair them and make boots out of this pre-soaked material.
The resultant boot was water resistant and would be used out on the ice. Snow goggles were carved out of wood and ivory. The narrow eye slits served a dual purpose, both to protect the eyes from glare and prevent snow blindness, and to encourage the wearer to squint, which gives better distance vision.
Good dogs.
Today's clothing is still about staying dry and staying insulated from the cold.
The whole way insulation works is trapping air. You don't heat the fiber, you're heating the air. A really warm jacket, if you've got 2 inches of insulation, here's your skin, it'll move that freezing point out to right near the edge of the outer fabric on your garment. Because when you're going from 80 above inside your garment to 50 below, you've got 130 Fahrenheit temperature change in 2 inches.
Though down and wool are still common insulators, the most prevalent insulating fiber is polyester fleece. In 1981, Aaron Feuerstein and his staff at Malden Mills pioneered a new manufacturing process for this product. By precision shearing both sides of the knit polyester to the same length, they were able to turn fleece into a durable, warm, man-made insulator. Moisture reduces the effectiveness of any insulator, and polyester fleece has proven efficient at drawing perspiration, which lowers body temperature away from the body. But fleece alone doesn't solve the problem.
If you're working up a sweat, you need to realize that you are, and before you do that, you need to take layers off.
Once you've got your insulation, you'll need a good outer shell to cut the wind.
50 below is such a magical temperature because you can take some fabrics out that are rock solid at room temperature, 70 above. You take them out at 40 below, 50 below, and you can rip them like paper.
This kind of gear testing is essential for people whose lives depend on it. Like professional dog musher, Ali Zirkle.
When you're out on a sled, 85 miles from the nearest village, nowhere near any kind of generator source, you have to stay warm or you're going to be in a tricky situation.
Ali's cold weather attire is carefully chosen and has all been extensively field tested. When she's dressing for competition in the cold, Ali's underlayer starts with wool shorts, followed by polyester long underwear, wool socks, and polyester wrist warmers. Her next layer consists of sleeveless expedition weight bibs with a fleece top. Layer 3 consists of a pair of neck gaiters, a fleece jacket, and a mid-layer pair of nylon pants. Her outer layer contains Gore-Tex shell wind pants, a -50 Fahrenheit parka with a beaver or wolf ruff, an anorak nylon shell, breathable wool boots, and fleece gloves. The finishing touches are a pair of overshoes, beaver mitts, a beaver hat, and a headlamp. Her dog team comes by their insulation with a little less effort.
Alaskan Huskies have a double coat, kind of the same thing as a wolf has. It's an underlayer of a thick furry layer, and then the outside layer is guard hairs. So that's why these dogs can live out in 40 below and do all right.
The dogs themselves haven't changed much over the years, but the sleds have. Early Eskimo materials, including wood and bone held together with caribou hide, have been replaced by lighter and more durable aircraft aluminum, held together with nuts and bolts.
You ready?
Ali's sled is packed to be lightweight, but to efficiently carry the obvious, sleeping bags, dry change of clothes, dog food, stove. And the not so obvious.
Most of the time in the Arctic, it's real dark. This is just one of the headlights that I actually carry. When I go out on a long race, 1,000-mile race, I'll probably have 2 or 3 backup headlights and some pretty hardcore lithium batteries. Obviously, staying warm is the issue. We do use a lot of chemical heat warmers. We'll pack quite a few of those.
These heat packs are activated by opening the package and exposing its contents to air. The warmers contain chemicals that oxidize iron and release heat. Staying warm and dry in the extreme cold is half the battle. But getting around successfully is the other half. If you have to travel in sub-zero conditions, ice can be a real killer. Synthetic fleece is made from finely spun plastic fibers. Approximately 25 2-liter plastic bottles can be recycled to make one fleece jacket. Sub-Zero will return on Modern Marvels. In cold conditions, there's a subtle boundary that's quite real. It can be found at 0. 0 is the liminal point between positive and negative. And on the Celsius scale, it's the line between water as a liquid and as a solid, ice.
It's tough to solve icing problems. It's an unusual material. It's tenacious. Ice sticks to everything so well. It expands as it freezes, so it destroys things. So it's a wonderful, beautiful, and exceedingly dangerous and difficult to deal with problem.
The line at which water turns into ice is also the line at which transportation becomes treacherous.
Halloween 1994, a commuter aircraft, Aerospace Shuttle ATR-72, was in a holding pattern over Indiana, and during that time they were icing. The de-icing boots were causing ice to pop off the wing. But when you have a large amount of liquid water, the conditions are warm and the droplets are large, it freezes slowly.
The plane was equipped with de-icing boots, inflatable rubber strips on the leading edge of the wing that fill with air and break off accumulated ice. But water ran aft, froze, and formed a ridge behind the boots. The ice buildup didn't impair the plane until its descent, when the flaps were raised. Airflow was altered, and a jump in the aerodynamic flow over the wings affected the control surfaces, the ailerons.
And it caused something called aileron snatch, where aileron popped up, and the airplane then went into a deep roll. I think it was a 70-degree roll. They corrected it, and finally it rolled over on its back and went down nose first.
Millions of dollars a year are spent de-icing planes and helicopters on the ground with propylene glycol, a freeze-point depressant that melts existing ice and lowers the temperature at which additional water will freeze.
Propylene glycol is sprayed on aircraft at very high temperatures, usually around 170 degrees Fahrenheit. But one jet can require several thousand gallons of de-icing fluid at the cost of $7 a gallon. So it costs a lot of money to de-ice an airplane.
But there are promising, less expensive alternatives, like infrared de-icing, which uses the heat from infrared light, long wavelength light, not visible to the eye, to melt off the ice. But it takes longer to de-ice with infrared technology than it does with glycol. Icing is an equally dangerous transportation problem in the ocean. But in this case, it's the weight, not the shape of the ice, that's the issue.
That ship bow plunges into the waves, you create a giant cloud up over the ship. And that water freezes on the ship if the temperature is cold enough. And because the ice is forming up above the center of gravity, as that ship rolls, it rolls more slowly and it rolls farther each time. Further and further. Eventually, if enough ice accretes, the ship will roll and it doesn't recover, and it goes over.
The technique for de-icing a ship is an old-fashioned one that removes the ice without doing much damage to the ship's paint job.
The way it's been done traditionally and the way it's done today is with baseball bats. And not any old baseball bat. It's a wooden baseball bat.
Ship icing is unpredictable, but some ice events are a given. Each winter, fast ice, sea ice that is attached to land, forms in the Ross Sea and blocks the resupply of McMurdo Station, the central transportation hub of the U.S. Antarctic program.
The ice can extend anywhere from McMurdo from a low of about 15 miles to upwards of 80 to 90 miles, and we have to break a channel through that ice to get those resupply ships in and out.
The task of breaking through to resupply, called Operation Deep Freeze, falls to the two strongest conventionally powered icebreakers in the world: the Coast Guard's Polar Sea and Polar Star, both commissioned in 1976.
We have a combination power plant of turbine engines that produce a tremendous amount of horsepower and diesel engines for normal cruising. Our turbine engines can produce a 60,000 horsepower with a burst up to 75,000 horsepower. It gives us the ability to ride up on the ice. The weight of the bow falls down. The flotation of the stern actually lifts up. We kind of get a hammering effect.
The polar icebreakers can continuously cut through ice to a depth of 6 feet at 3 knots. Typically, each vessel makes the Antarctic journey in alternating years and begins breaking the channel around Christmas Day. But recently, because iceberg B-15A shifted its position, blocking currents and causing a buildup of sea ice, both vessels were on hand to ensure that the vital resupply at McMurdo Station was completed by mid-February. From McMurdo Station, supplies are flown 850 miles onward to the South Pole Station on LC-130 cargo planes. The National Science Foundation is attempting to find an alternative to this costly link in the transportation chain by charting a trail between the two bases.
An overland traverse provides the opportunity to deliver non-perishable goods with tractors and sleds, mainly fuel. And it's very inefficient using aircraft to deliver fuel. For every 3 gallons of fuel an aircraft burns, they deliver about 2 gallons of fuel.
Begun in 2002, the South Pole Traverse covers a 1,000-mile path from McMurdo Station on Ross Island to the South Pole. The path crosses the Ross Ice Shelf, heads up the Transantarctic Mountains via the Leverett Glacier, and then continues a final 150 miles to the South Pole.
We have 85,000-pound vehicles traveling from McMurdo to the South Pole, so safety is a primary concern.
The trail is riddled with crevasses, splits in the ice ranging from 70 to 120 feet deep, which are deadly because they're not readily visible. Their surfaces are bridged by a thick covering of snow. As a result, the trail had to be prospected both by helicopters and snowmobiles, using ground-penetrating radar to chart a generally safe path.
Our technique is to use dynamite and basically expose a hole big enough for a mountaineer to drop inside, get the actual internal dimensions so we can determine a volume we need to fill it.
Fill, in this case, is snow.
The longest part of the entire task wasn't filling the crevasses. It was actually identifying safe areas for the bulldozers to operate.
But it's not only in Antarctica that safe transportation at low temperatures is challenging.
It's really difficult to describe just what happens to an automobile or to almost anything in the world at 40 degrees below zero. Lubricants become stiff, motor oil becomes stiff, batteries become weak.
In cities like Fairbanks, Alaska, when it gets cold enough, drivers plug in the engine warmers beneath their cars' hoods so that fluids and batteries will stay warm, or their cars won't start. One local company is marketing a retractable cord reel to make this job just a little easier in the cold.
The Arctic Leash provides 110 voltage to the vehicle. Within the vehicle, there's an adapter. We have a cord that goes to a battery blanket. We have an additional one that goes underneath the engine to the oil pan, and then one that goes into the engine block that keeps the engine warm. Granted, it's just an extension cord, but it's the only all-weather retractable cord reel in the world.
Snow and ice do present a daunting challenge for transportation, but there have always been people who can't wait to get out on this sea of white. If you want to go in the snow, the snowmobile is the vehicle of choice for work and play.
I have a cabin that's 3 miles from a snow park, so we rely on the sleds to get in. We have utility companies that buy the snowmobiles to get to remote cell sites.
Though early motorized snow vehicles date back to the 1930s, it wasn't until the 1950s, with the introduction of smaller gasoline engines, that 1- and 2-passenger snowmobiles were sold, and recreational use began. Polaris came out with their first snowmobiles in 1954. Today, 4 manufacturers will sell over 200,000 snowmobiles in the United States, Canada, and Europe. In remote areas lacking roads and plows, dog sleds have been replaced by snowmobiles as the functional vehicle of the backcountry. A snowmobile's spinning track propels the vehicle and keeps it aloft in the snow. The skis provide steering and additional lift. Today's sleds pack quite a bit of punch.
World record speeds on snowmobiles is right around 150 miles an hour. You can get them up and over a lot of terrain, but easily, consistently 40-degree slopes that they'll climb up.
Comfort has come a long way as well.
We've got things called hot doggers, or little ovens that you can put on your exhaust pipe, put food in them, warm the food up.
A hot meal is always welcome in the cold. But in the Arctic, a little heat can be a dangerous thing. On the Trans-Alaska Pipeline, permafrost gets a little help to stay permanently frozen. During Operation Deep Freeze's yearly resupply of Antarctica's science stations, 8 million gallons of fuel and 11 million pounds of cargo are delivered to McMurdo Station. Sub-Zero will return on Modern Marvels. Throughout the world, ice appears in myriad shapes and forms. But where industry and infrastructure are concerned, ice's role is not so varied. It can be cleanly divided into 2 camps: ally or obstacle. In the case of Alyeska's Trans-Alaska Pipeline, hundreds of miles of ice frozen in the ground were one of the primary obstacles to moving 14 billion barrels of oil from Prudhoe Bay to the port of Valdez.
The permanently frozen ground that the Trans-Alaska Pipeline traversed had to be traversed in a manner that would not allow the permafrost to degrade to the point to where it would become soft and would no longer support the pipeline.
One of the solutions was to build half the pipeline over the 400 miles of permafrost-affected area above ground, separating the hot oil in the insulated pipe from the icy foundation below it.
The liquid is about 104 degrees coming out of Prudhoe Bay, and it is about 30 degrees colder by the time it arrives in Valdez.
But insulation and separation weren't enough to ensure that the permafrost would stay frozen. Alyeska's engineers turned to thermosiphons, closed pipes with refrigerant inside. The 120,000 thermosiphons on the pipeline remove heat from the soil and transfer it to the air.
The heat in the permafrost evaporates the ammonia liquid, and the ammonia ascends the column. Then in the wintertime, at the very top of the heat pipe, the ammonia condenses into a liquid and rejects its heat to the atmosphere.
The air temperature must be below the temperature of the permafrost, 31 degrees Fahrenheit, to be cold enough to condense the ammonia vapor and return it to soil level so that the cycle can continue. As a result, this passive system only operates in winter.
So the concept is that you want to remove as much heat as you possibly can in the wintertime so that it can carry through that frozen ground to the end of summer.
Elsewhere in the National Petroleum Reserve, 23.5 million acres of public land on Alaska's North Slope, Ice is an ally rather than an obstacle to oil exploration. Companies like Peak Oilfield Service build ice roads. Roads made of shaved ice from lakes and sprayed water to take oil rig components out to remote areas on the North Slope.
There's a tremendous environmental benefit to building an ice road as opposed to a traditional gravel road. For one thing, you utilize resources around you, freshwater lakes. You use snow and ice chips off of the lakes. And then when it's all said and done, it simply melts.
The ice roads provide routes to little-known areas where companies are drilling exploration or wildcat wells.
So for a company to go out there and not really know what's there, it's not economical to build a gravel road 60 miles out and then come up with nothing.
The process begins with an initial pass in which the route gets its first coat of water. The next step is similar to standard road construction.
We'll get onto lake surfaces and we will trim ice and we will gather snow and haul it conventionally, similar to a gravel construction, but we'll be using either ice aggregate or snow. Each time we put the ice aggregate or snow in place, we'll add water to it and we'll use graders and blade it to form the template that we want.
Trucks carrying more than 6,000 gallons of water cap the road with a smooth coating of water that quickly becomes ice. The finished product is a road capable of carrying surprisingly heavy loads.
We've carried loads in the neighborhood of about 1 to 1.5 million pounds. And these loads are rig modules. This last week, our temperatures were probably in the average of minus 25. You have a tremendous amount of traction on that ice when the temperatures are that cold. Of course, in the springtime, and as the sun starts to come up more and more, it's like standing on a skillet. I mean, it's slippery.
And that slippery ice is their signal that it's time to leave the road and let it melt away. While most people look forward to a spring thaw, for some communities, melting ice can be devastating. An ice-blocked river can flood in moments after a spring rain or snow melt.
The ice cover will break up and run downstream, and then you can get ice jams in the river where the ice transport capacity of the river isn't sufficient to carry the ice, or the moving ice hits an intact ice cover. What happens is the upstream water levels rises and it can cause overbank flooding. We have techniques for weakening the ice downstream. If we know the ice run will come down and it will collide with the intact ice cover, if we can weaken that ice cover, we may let the ice go right through the area where the flood will occur. And in that case, we may cover the ice with dark material so that it melts faster, or we have techniques for going out on the ice and cutting slots, drilling holes, and other means for weakening the ice ahead of time.
At the Army's Cold Regions Research and Engineering Laboratory in Hanover, New Hampshire, river ice control begins in the lab.
We actually have models now that will model each individual piece of the ice jam. They're called discrete element models, and they may have many thousands of ice pieces, and we'll model each individual piece as an ice jam forms in the computer, and we can see what the impact is on the upstream stages and on the flows from this type of model.
Sticky problems like river ice often receive complex solutions. But out in space, the Cassini spacecraft solves its issue with the cold in a simple fashion. It hides behind a warm blanket. In 1975, the Trans-Alaska Pipeline's peak construction year, over 28,000 were employed by Alyeska. In the 2 years it took to build the pipeline, 31 were killed in accidents. Sub-Zero will return on Modern Marvels. Two agencies oversee much of the U.S. science initiative that takes place in the cold. The Office of Polar Programs at the National Science Foundation and NASA. Their jurisdictions are respectively the polar regions here on Earth and the universe. Since Antarctica is remote and cold, it's often used as an analog for space. Temperatures outside the South Pole Station, minus 100 degrees Fahrenheit, and outside the International Space Station, minus 140 degrees Fahrenheit, are close enough for discomfort. Fueled by energy from an array of solar panels, the station's electronic equipment generates the heat that keeps it warm. In addition, the station is insulated by a highly reflective blanket made of mylar and Dacron that rejects solar radiation while preventing cold from penetrating. Such blankets can also be found on the Cassini spacecraft, which was launched in 1997 for a 7-year, billion-mile journey to study Saturn, where temperatures average minus 300 degrees Fahrenheit. Cassini's thermal blankets, consisting of 24 layers, including aluminized Kapton, mylar, and Dacron, cover the 3-story tall spacecraft from top to bottom.
Typically, the way it's done is you'll take sheets of brown patterning paper and they tape this up to the actual spacecraft hardware, and they're bending it around and making nips and tucks, and then they'll take rolls of this metallized reflective foil and just keep stacking the material upon one another and then sew the edges together to produce a durable multi-layer insulation blanket.
Before leaving Earth, Cassini was temperature tested at NASA's Jet Propulsion Laboratory.
You're standing in front of JPL's 25-foot space simulator. It does cryogenic temperatures down to liquid nitrogen temperature, which is minus 185 degrees centigrade.
After completing its long journey to Saturn, Cassini released its probe, Huygens, on Christmas Eve 2004. The probe has sent back data and photos of Saturn's moon, Titan, frozen at minus 290 degrees Fahrenheit. Another unmanned probe has been going through its paces here on Earth. On January 24, 2004, a balloon-shaped robot explorer, the Tumbleweed Rover, completed a successful 8-day, 40-mile wind-driven trip across Antarctica. The craft's mobility didn't shock its designers, since the concept for the rover was derived from a wind-related accident on another craft.
They were doing some testing out in Mojave Desert. While they were out there, the wind started to pick up. One of the wheels broke off the 3-wheeled rover, and they had a hard time chasing this thing. And that's where they had their idea. Wow, why don't we just instrument one of the wheels and see what we can do with it?
The result of this accident was an 88-pound, 6-foot-tall inflatable that can carry a variety of instruments in a PVC pipe that spans its diameter. The instruments gather topographical and environmental information. The rover may one day roll across the frozen surface of Mars, but first it had to pass cold tests on Earth. Warmed by the heat of its own electronics, the rover kept its internal instrument payload at 86 degrees Fahrenheit, while the temperature of its Antarctic surroundings averaged minus 22 degrees Fahrenheit. At the opposite end of the world, in the cold but fragile Arctic, an international team of scientists working with the National Science Foundation is attempting to understand warming trends in Arctic waters.
I like to think of the analogy of a heart. Heat gets pumped up to the Arctic and fresh water gets pumped down. And exactly where that fresh water in the form of river water and ice melt ends up back down in the Atlantic Ocean has a strong impact on how the ocean circulates and on our climate.
In addition to floating buoys that transmit data from the moving ice pack, scientists have installed a mooring in a fixed position, stretching 2.5 miles from the ocean floor. 17 instruments have been attached to the line, including current meters, sensors to measure ocean temperature and salinity, and at the top, sonar to measure the draft of the ice.
The big changes are basically that the water coming in from the Atlantic Ocean is a lot warmer than had ever been seen before by several degrees.
And the waters just beneath the pack ice are changing as well, exposing the ice to increased temperatures. Just as we sometimes suffer in the cold, we will certainly suffer in its absence. The globe's climate is a delicate balancing act, and it's through close observation of these coldest of places that we truly measure the vital signs of the planet. And it's through our direct experience of the cold, when we work in it, inhabit it, and play in it, that we can appreciate its icy gifts.